Hello everyone, welcome to the lecture 3 of EC573 Advanced Embedded Logic Design Winter 2022 semester. In the previous lecture, we discussed about the hardware software co-design and we discussed about the various requirement of the bus protocols for the heterogeneous system on chip. In the today's lecture, we are going to focus on the AMBA, that is the Advanced Microcontroller Bus Architecture. And inside the AMBA, we are going to focus on the AXI4 protocol. So a few details that our lab timing is changed from 4 p.m. to 7 p.m. on Friday instead of the 3 p.m. to 6 p.m. Before the Friday's lab, make sure you install the Vivado with SDK 2019.1. The details are available on the Classroom. If you need a desktop, please submit a form on the Google Classroom. And again, how to access the remote hardware, the details are already uploaded on the Google Classroom. For any queries related to the software installation, software issues, desktop access, and hardware access, you should contact the TS. For any queries related to the lecture topics as well as lab topics, technical issues, doubts, you can contact either instructor or the TA during their office hours. So in the AXI stands for Advanced Extensible Interface, and it was introduced to support the high throughput communication. Inside the AMBA, AXI is the one protocol, but you have the additional protocol such as APB, Advanced Peripheral Bus Interface, AHB, Advanced High Performance Bus Interface, ATB, Advanced Trace Bus. In the AXI, we are going to study the three subtypes: AXI4 memory mapped, AXI4 stream, and AXI4 light. In the AXI4 protocol, you just need to study the AXI memory mapped in detail, and the other protocols are the subset of the AXI memory map. So once you study the AXI memory map, you don't need to re-study the AXI4 stream and AXI4 light protocol. So whenever I mention AXI4, I am talking about the AXI4 memory map. For AXI4 light or the stream, we will explicitly use the term light and stream, but for the memory map, we can use the normal AXI protocol. So AXI protocol allows or highlights how the data communication can take place over the AXI link. So in the AXI link, so suppose that you have the two IPs or two units, say A1 unit and the A2 unit. Then suppose you want to send the data from A1 to A2 or from A2 to A1, you can make use of the AXI protocol. So you can see that this is the AXI link between the A and B. It is a multi-bit thing. So on the AXI link, only one unit can be master and another unit become a slave. So for example, right now we can assume that the A1 is master and A2 is slave. Over the link, there are two transactions can happen. One is the read transaction and the second is the write transaction. In the read transaction, master reads the data from the slave. In the write transaction, master writes the data to the slave. So in a AXI link, you can support two types of transaction: AXI read transaction and AXI write transaction. On the AXI link, the master initiates the transaction. Slave cannot initiate the transaction. Only the master can initiate the transaction. Slave will only respond to the transaction. And what is the transaction? It's a transfer of data from one point to the another point. Okay. So In the AXI, as we are talking about, there are AXI link. Inside the AXI link, you have the read and write transactions. And to support the write and the read transaction, you have the channels. Okay, so we are talking about now channels. So for the read transaction, you have two channels. One is the read address and control channel, and the second is the read data channel. So in the read transaction, the master is reading the data from the slave. So master sends the address and control information to the slave, and the slave sends the read data to the master. Similarly, in the write transaction, there are three channels. One is the write address and the control information. Second is the write data, and then you get the write response. So via using the write and address and the control information, master tells the slave that I want to perform the write operation at this address with this much amount of data, with this type of data, and so on. Then the master sends the data on the write data channel, and then after the write operation is completed, slave sends the response whether the write is completed successfully or there is an error or something. The response is sent from the slave to the master. So the each channel may carry the additional information that describes the parameter of the transaction. So that's why we say that the address and control information. Now each one is the multi-bit. Okay, each channel is a multi-bit. So you may have the multiple types of data inside the each channel. Also, you need to understand that the read transaction has separate channels and the write transaction has the separate channel. So at a time, you can have the simultaneous read and the write transaction between the master and slave. So it is not limited that on a one AXI link, you can have either read or write. Since the bus I is parallel, you can have both read as well as write in parallel. So in the AXI memory map, you have the read transaction and write transaction. And in case of the memory map, you support the burst transaction. Means for a single address and the control information, you can transfer or receive the multiple data. For example, for one address and control information, you are receiving the multiple data. And this is called as a burst transfer. And it will help us to give the higher throughput because for every address and control information, you are wasting the time for the actual data communication. That's why your throughput gets affected. So in the real scenario, in the burst transfer will help you to get the higher data throughput. In case of the write transaction, the master sends the address and the control information. Then the master sends the multiple sets of data. And then after the write operation is completed, slave sends the response. Okay, so this is how the read and the write transaction takes place. So AXI4 provides the separate read and the address connection for the read and write, which allows multiple bidirectional data transfer. So your read and the write transaction can happen in parallel. When you are doing the read transaction or the write transaction, overall philosophy remains the same. First, the address comes out. So in case of the read transaction, master sends the address from which the data needs to be read. In case of the write transaction, master sends the address from which the data at which the data should be written. Then the data is either written by the master in the write transaction or provided by the slave in the read transaction. In case of the write transaction, you have the additional channel, which is the write response channel, which allows the slave to tell the master that what is the status of the write transaction, whether the write transaction is successful or not. So as you can see, it's a protocol. it will be implemented in hardware. So you can't have the burst of the infinite size. So in the AXI protocol, the burst size can vary from 1 to 1256 data transfer. And what is the burst size? The number of transactions. For example, in this case, the burst size is 4. For one address, you have the 4 transaction of the data. And this is called as a burst size. Now, what is the size of each data? So this size in the AXI protocol, it can be 1 byte, it can be 2 byte, it can go up to 128 bytes, that is 1024 bits. But in the Xilinx FPGA, they don't support all these possible size. They support only 4, 8, 16, and 32 bytes. Okay, these are the only transfer sizes supported in the Xilinx FPGA. Okay, about the AXI Lite and AXI Stream, we will discuss it later. We will focus it on a AXI memory. So, for example, whenever the master want to send the data to the slave or read the data to the slave, master will use the control information to communicate the what is the size of the burst. It can be 1 to 256. Then master will also communicate what is the size of each transfer. It can be 1 to up to 128 bytes in case of the normal AXI4 protocol. In case of the Xilinx FPGA, it supports only 4, 8, 16, and 32. Okay. Now, suppose that you have this master, which is here, and then you have the slave, and then this is the AXI link. Now, suppose that the master wants to send the so suppose that the this one, the burst size, the burst length is say 2. Okay, so that means for every address, I'll have the 2 sets of data, and then the transfer size is say it is fixed to the say 4 bytes. So you can say that each transfer is equal to 4 bytes. So total will be equal to the 8 bytes. Now this master wants to send the 7 bytes. So how it can send the 7 bytes? It can send the 4 bytes in the first one, and then 3 bytes, or vice versa, 3 and 4. But how this slave knows that out of the here, because your size of the data bus is 4 bytes, how the slave knows that the only 3 bytes are valid? So to enable such kind of transaction, you need a additional signal. So in the AXI protocol, you have the transactions, then you have the channels, and to support the corresponding transaction or functionality of the particular channel, you have the additional signal. One such signal is a byte length strobe signal. So by using the strobe signal, which is 1 bit for every byte, you can master can tell which data is valid and which data is invalid. So for example, in that case, you have the you have the data, each of the 4 bytes. So here the strobe signal can be FF, that is 1111, indicating all the bytes are valid. And here it can be 7, which is the 0111, indicating out of 4, only 3 bytes are valid. So by using this additional signals, you can enable the more efficient transfer of data. And this byte-wise type enable signal is very important on the heterogeneous SoC when you want to integrate your microcontroller or microprocessor with the different units inside the SoC. We know that the microcontroller and the microprocessor works on a 8-bit boundary. So that means they are going to transfer the data in a bunch of the 8 bits, 16 bits, and so on. And so it is when you want to communicate with the other units who works on the who are not limited to the 8-bit boundary, this byte length strobe enable signal is quite useful. So till now we discuss about the AXI interconnect between the two units, which is the A1 and the A2, and you have the master and the slave port. Now here you can have the another AXI link, where this is the master and this is the slave. So single unit can become a master as well as the slave. Now if you have the multiple masters and multiple slave, how your design will work in this scenario. For example, here you can see that I have the 3 masters and I have the 4 slave. One option is that I can have the independent AXI link between every master and every slave. So in that case, I'll have the 12 links of the AXI to enable the communication between every master and every slave. But another way is that I can use the interconnect, and these masters and slaves are connected to the interconnect. And in this case, you can see that if this masters wants to communicate with the slave, here on this port, this guy is a master, this guy is slave. So you can have the one AXI transaction. And then on this interconnect, on this link, interconnect is a master and this guy is a slave. And this is another AXI transaction. So your AXI transaction is broke down into the 2 AXI transaction. One from master to interconnect and then second from interconnect to slave. And in this case, you may have the additional latency, but the advantage is that instead of 12 links, you will need only the 7 links. You can see 1, 2, 3, 4, 5, 6. So this is the trade-off between the hardware resources and the corresponding latency. And you need to, as a designer in the chip, you need to take a call how many interconnect or how many one-to-one links you need. But use of the interconnect is quite very common, and in addition to the routing of the data from the master to slave, it performs a lot of other tasks which we'll study in the detail in later. So we discuss about the AXI link, we discuss about the AXI transaction, read and write. Then we discuss about the channels, read, address and control, read data, write, address and control, write data, and write response. And then we also discuss that to support this each of the channel, there are additional signals. Now, what are these additional signals? It will take a few slides to discuss all the signals. But we will first start with which are the minimum signals which you should know. So, for example, if we consider the read, address, and control channel. Okay. So in the read, address, and control channel, you are going to pass the information. Which is this information? It has the address information and the control channel. Okay. And along this information, which we also call as a data, that useful data, you will have the additional signal. The minimum important additional signals are valid, which we discussed in the last lecture, importance of the valid, and the ready, which is equivalent to the acknowledgement, which we discussed in the last lecture. Then you can have the additional signal to indicate size of the burst, length of the burst, quality of service, and others, which we'll discuss it later. But in the minimum case, you will have every channel will have the 3 signals. One is your information signal, second is your valid signal, and the third is your ready signal. For example, in case of the read data, you will have data as an information signal over which actual data is transmitted, then the valid, and then the ready signal. Okay. So each of the independent channels consist of the set of the information signals along with the valid and the ready signal that provides the two-way handshake. So for example, here, in case of the write data, you will have the information signal, which is the data. Along with that, you will have the valid and the ready signal, which will provide the handshake between the master and slave. What is the handshake? The point at which the data is transferred from the master to the slave. So the information source uses the valid signal to show when the corresponding data is valid on the data bus. The destination uses the ready signal to indicate when it can accept the data. So whenever the valid is 1 and the ready is 1, handshake happens and data is passed from the information source to the destination source. So for example here, in this case, you can see that the information source has put the information on the information bus at this point, because at this point, the information source has made the valid is equal to 1. Then the destination has become ready at this point, and then you can say that at the next positive edge of the clock, the handshake happens at this point, and the information is assumed to be transferred from the source to destination. Who is the source in the right response? In case of the right response, you can see that the slave is the information source and the master is the information destination. So here slave will put the data on the bus, slave will generate the valid signal, and then the master will generate the ready signal, and the transfer of data will take place. So the source generates the valid signal to indicate when the address, data, or the control information is available. The destination generates the ready signal to indicate when it can accept the information. Transfer happens only when both ready and the valids are high at the positive edge of the clock signal. Few important points about the ready and the valid handshake. Source is not permitted to wait until the ready is asserted before asserting the valid. What does this mean? Whenever the source wants to transfer the information, source should not wait for the ready signal to become high before making the valid signal is equal to 1. This is because it may happen that the destination is waiting for the ready valid signal to become high before making the ready is equal to 1. So to avoid such deadlock, the AXI protocol says that whenever the source has the data to be transmitted, source should put the data on the information bus, source should make the valid is equal to high, and then wait for the ready to become high. Once the valid is asserted, it must remain asserted until the handshake happens. Okay, so whenever the source puts the data on the information bus and the make the valid is equal to 1, it should make the valid is equal to 1. It should retain the valid is equal to 1 until the handshake happens, and the handshake will happen when the ready becomes 1 and at the next clock edge. A destination who is controlling the ready signal is permitted to wait for the valid signal to be asserted before asserting the ready signal. So the destination can wait till the valid signal becomes 1 before asserting the corresponding ready signal. So the ready signal, the destination has a complete freedom to make the to assert or deassert the ready signal. But there is a one requirement. When the destination makes assert the ready signal, if we find that the ready valid signal is not high, then the destination can put the ready signal down. But when the destination asserts the ready signal and there is a already valid signal is high, destination has to accept that data. Destination cannot ignore the data. So there are multiple ways, multiple scenarios can happen between the ready and valid handshake. In this case, you can say that the source has put the data and on the data bus, and source has made the valid is equal to 1. Then source has to wait till the ready becomes 1, and then the handshake takes place. In the second case, you can see that the source has put the valid signal and the corresponding data on the data bus, and the destination is already ready. So immediately the handshake happens. In the third case, you can see that the source has put the data on the information bus, where source has asserted the valid signal, and at the same time the ready has also been asserted by the destination. So immediately at the next clock edge, the handshake takes place. So there are multiple ways. So now let's look at the timing diagram. So the first thing we need to look at the timing diagram is to identify whether it's a read transaction or the write transaction. And by looking at the signal name, you can see that this is the read transaction. When the name signal name start with AR, it corresponds to the your address and control information for read transaction. Okay, when it is R, it is nothing but the data channel. Okay, data channel for the read transaction. So you can see that in the beginning, in case of the read transaction, the master will put the address and control information, and source will so the slave will send back the data. So master will put the address and control information. I'm just keeping only the address information. The control information, other additional signals, I'll add those after later, so that once you are comfortable with the AXI protocol. So here the master or the information source puts the information, then information source put the valid signal. So who is the information source here for the address read and control information? It's a master. Then the information source wait for the information destination, which is nothing but the slave, to make the ready is equal to 1. And at this point, the handshake happens, and then the information, which is this one, is being transferred from the source to the destination. And at this point, the slave knows that there is a request for the read transaction, and with the address and the control information, which is embedded here. Then the destination, which is then the slave reads the data. The slave takes the first bunch of data, puts on the data bus. Then slave makes the valid signal 1. The master is already ready, so the first bunch of data is transferred. It's a bus transfer. So for one address, there is a multiple data transfer. Slave takes the next bunch of data, makes the valid is equal to 1. Master is already ready, so the handshake takes place. Slave takes the next bunch of data, makes the valid is equal to 1. Master is already ready, then the next handshake takes place. Then slave takes the next bunch of data, makes a valid signal, and at the same time, slave also makes this additional signal, which is the last signal. And this indicates that to the master that this is the last data of this particular transaction. And then the master makes the ready is equal to 1, and the transaction takes place. So usually with the data signal, write data or the read data, you have this last signal, which is indicating that the transfer of final data in the transaction. So as I told you, the data, ready, and the valid are the the 3 important signals. But in addition, there will be additional signal like strobe signal, last signal, and so many additional AIRD, length, size, and so many signals will be there to support the transaction. I'll introduce the other signals one by one once you are comfortable with the read transaction. So now look at this next example. So here you can see that this is also a read transaction because your signal names start with AR and R. Now in this transaction, you can see that the master puts the address and control information, master puts the valid signal, and the slave puts the ready signal. And at this time, the transaction A is accepted by the slave. So slave knows that it needs to perform the read transaction. Then the master puts the another transaction request, again puts the valid is equal to 1, and then the slave also makes the ready is equal to 1. That means at this point, slave also accept the another read transaction. So now at this point, you can see that the slave has the 2 read transaction requests. Then slave first complete the first transaction, which is consist of the burst length of 3. Then it generates the last signal, which indicate to the master that this transaction is completed. Then slave perform the second transaction, generate the last signal to indicate the master that second transaction is also complete. So master can send the multiple transaction without waiting for the previous transaction to be over. Slave can also accept the multiple transaction before completing the ongoing transaction. It all depends upon how you have designed the master and the slave. Some slaves support the transaction, multiple transaction. Some slaves may reject your transaction when they are already doing there is already one ongoing transaction. Okay, so it all depends upon the how you write a code for the slave and the master. So in this one, you can see that there is a additional this is the another timing diagram, and here you can see that your signal name start with the AW. So what does this means? AW means it's a address, write, and the control information. So here you can see that the master puts the address information, master puts the valid signal, and then the slave puts the ready signal. And at this point, master slave knows that there is a write transaction request from the master to the slave. Then in the write transaction, there are three channels. First is the address, write, and the control information. Then you have the write data channel. Then the master puts the data on the information bus. Master puts the valid is equal to 1. Slave becomes ready. Slave accepts the first chunk of data in the write transaction. Similarly, second chunk of data and so on. And then using the last signal, master tells that I have transmitted all the data for this transaction, and now you need to write the data. Then slave takes the data, perform the write transaction, and then reply over the write response channel by putting the information whether the write transaction is okay, not okay, corresponding valid signal, master is ready, master accepted, and here your write transaction complete. So in case of the write transaction, information source puts the address, information source puts the control data information, and the information destination will give back the the outcome of the transaction. So to summarize, you can see that in all the 5 channels, you will have the information bus, but to support the information bus, you will have at least bare minimum 2 signals, valid and the ready. So for write address, the corresponding each ready and valid will start with the AW. In case of the write data, it will start with the W. In case of the write response, it starts with the B. In case of the read address, it starts with the AR, and in case of the read data, it starts with the R. Okay, so this completes the initial discussion on the AXI memory map protocol.